Okay, good afternoon. So today we will try to hosting as the online. In this format, as usual, I will always like record it as a Zoom. So if you're not attending the class, like in this moment, you are totally fine, and then you can watch it later. Okay, and then they will I will try to always like host it as the same in the morning, and then we can start our class today. So just going back, suppose in the lab you already installed the VM, and then maybe you can choose the one if it's on your system. And we need to know some basic static techniques like we're going to cover. So for the static analysis, we need to know, okay, so what the actual payload. The payload will be we will say the content. So without like really executing it. And then based on this, then we can determine the functions and then the maliciousness of those we say potentially contain the malware. Okay. So what's the goal? Or like we like to do, we try to generate a file signature so we can able to identify those like common code or data used across the malware instance. Probably they will maybe, let's say we have the embedded URLs. So those may be like commands for control. We see, look, when we look at those like embedded URL, then we'll able to trigger, okay, maybe possible if we execute certain function and then we will redirect or like forwarding the data or information, sending those information to certain location, destination. So this got an embedded URL. And then some common code, such as like decryptions or network scanning. So it's going to the network scanning, including will be the codes for looking for the devices connected hardware, and will be possible doing this way. And then the communication artifact such as like strings or constants. So that's what we're looking for. Okay, and right here, typical way we try to do for analysis is the static file signatures without a signature. So we try to identify through the like search of the binary. Um, it's a pretty same idea when I talk about the patterns of the virus, like how the anti virus is what they are scanning. So it's more static before we really execute it. So let's say for the string search, so they were looking for some consecutive characters, maybe in the 7-bit ASCII code. So if you know the ASCII code, so for like, let's say we have a B, A, and they refer to 42, 41, and then they have their range. So we can like terminate by a null. So we say, okay, they end by null. So just like this, so they represent a string. Okay, it means like bad. Okay, so it will be like 42, 41, 44, and then come with the null. Or we can looking for some like consecutive 2-byte Unicode. So really depends on system. So we maybe have some like different potential string search pattern, maybe 7 bits or 2-byte. Okay, Unicode. So it can be combined together like 42 and then end with the 00 right here. So it will be 2-byte. And also it's the same result will be a bad. And then they also end with the null terminator. So it will be the same. So here is the all the target we possible to search for the string. Okay. And the signatures they also can like perform, we can using some regular expression. Regular expression, if you're writing a program that maybe you have slightly idea. So we represent using the /d w, or we can use some any like special character dot to match all the content, and that's how we going to do. And then one of the encryption method, you see the hashing, including the MD5 or SHA. I mean, the MD5 is like have the lower level, less secure and hashing method, and then SHA is more common we are using nowadays for the code session. So here's will be the static signature. When we try to search it, the possible letter tooth, later, um, after we install a VM, and also I will let you to try different type of tooth for doing the NSS, and later we'll go into cover in the lab. So then we're going to like disassembler and then the binary NSS tooth to and examine the binaries. Also, their link library. So it's mainly we call like phasing. Those like strings. So we will like put all the ASCII strings of a certain length. So something like base 64. All the content will really depends on the how we define most time maybe like base 64 string. So we're showing, okay, we have the command line, and then when we input, okay, let's say password comes in, you will know when we using the maybe like Ubuntu, when we SSH to log in, and then you didn't see any password, right? Okay. And when we try to put in some, like, let's say we have the try again, and then some certain password, and also certain as the other patterns keyword. So in this level, all the password can be like encoded in very common data format. Then you may find a string. So they will we can use that to produce this password. Mainly you can see red in color. So mainly like uppercase, lowercase, and with some numbers, other symbols. So they're all possible. And you will see pretty common with the end of the last file. So we will see exactly the like end of the last file binary and its session. You will see all these slightly patterns we are going to use, but you don't have to really memorize in this moment. So you just need to know, okay, so when we try to read it and then it comes out, we will look at the headers. So the header, most of the time we will handle with the hex, and it was showing what's the class like file like 32, and then what's the under system, maybe a Unix, and what's the machine, you will see the Intel. So you will see um old pretty old machine we are using is the Intel, and then what's the entry point address, and we have some like relocation session, including now for the offset. So we have different entries, and then you will see they including go for the session, we including the jump slot. So for jumping each session, and we have the symbol tables. So maybe we have different type of entries. So we list of this, and right here you will see the object dump and then object dump. So it's similar to the with the end of the last file, and then we often use like the quick disable the code session. So it's like looks like this, and then you see all the sessions, maybe 65 right here, number 65, 824. So 824, and then export pop, and then push, and then we have call. All this will come in. In this moment, you just get a rough idea. And later in the really practical, then maybe at the lab, then we see, okay, what we are looking for. And also we have the NM, and we try to find the symbols within the binaries, and also the library. So if we're using the NM to search it for it, and then maybe some like right here, data encode paste, then we're looking for it. Okay. And then we have the called the LDD, and then we can find the dynamic library dependency. So if let's say we have the LDD, and then looking for the user bin, and then let's this directory, then we can looking for the those dynamic dependence. If we try to load this content, and then it will list, okay, what the library, okay, it would be i30 86 Linux G and U, and then with the library SO6, so with the location. So this one is you see the syntax. If you're familiar with the like Linux system, maybe like Ubuntu, you would say pretty similar. So user bin or this directory. Then how about the one we can use like for Windows? We are going to check like let's say their binaries and their link library. Then we can use one is called the resource hacker, and for identify the string and facing the session and the individual resources record. So all this pretty similar. So we can read the like end of the file, also like with the like also the object and after we just like start the diagnose menu and then store, and then let's say here you diagnose with the calculator, right? So we will check. So in the diagram right here, you see if we execute and then looking for certain files, then we can see the execute, and with the function the PV view, then we can look at some different section of the binary figures. So for the memory, so you see or some file static, so we will really looking for the really let's say the distribution, the machine or sessions timestamp. Even though we have different OS, but we do have different way to looking for the headers. Okay, we will list it now. Okay, so pretty similar. Or the dependency worker, so we can find the share library. So it's pretty it's similar to LDD using for the Linux system. So we're looking for all those like related you will see the DLL. So it's we are using a lot for the Windows, and then those like libraries. And you will see different type of library. Maybe we need to know and get some basic idea concept about what's the DL using. Sometimes you will see the kernel 32, so just like really common DLL using maybe some core functionalities such as like access manipulations of the memory files or hardware. So in case if you figure something, okay, maybe the kernel 32 is not same as or normal, then probably they will have some code to like access or manipulate the memory. Okay. And also we have another one, we have the ADVAP by 32. So this one is the another DLL provide the access. So this one will be more like advanced, maybe for the window components, maybe the Surface Manager or the Virtually. So maybe the when we widgets certain surface or the task, then probably will be over there or login. And then the user 32, so will be some like user interface components, maybe like the buttons, scroll bar, or some other components that control the user action. So if this DLL, like for the user interface, maybe modify, maybe the buttons, when you click on this button, it will take another action. Then it's the way they can change the performance. So we need to like be careful of this part. And then another one, you will see the GDI 32. So this one will be the functions for the displaying or like manipulating the graphic. So this one, you're going to change what you see. Okay, so when we display and then the anti, so anti-DLL. So this one is using for the interface to the Windows kernel. So those like executable. So they may be not really import to the file directly, and maybe they will indirectly import to the kernel 32. That means you know the core function, and then maybe they will call it, and maybe they are executable imports to it too. So it really depends on. It means like the author, okay, they can like intend to use that functionality. They may be not like normally available to the Windows program. Sometimes if they're hiding some functions or manipulating some process, then they will use this DLL. Okay, so you will see they're working together, but it's kind of like indirectly applied to some certain functions. Okay. And then we have the WSOCs or the WS2, and then all this will be the networking. So maybe a program they can access either like maybe they maybe have a connection to the network, or so certain network related tasks to be like performed then maybe under the WSOC 32. So if we need to check, okay, if we are certain the connections network related, then we need to scan for this. Okay. And then we have the win in INET. So this one will be the higher level networking function. So including those like protocol like FTP, HTTP, or NTP. So all this will be the common DLL will be like possible. We will see when we list right here, that means like they will be the target we are looking. So right here you see if in case or when the attacker want to change the content. Okay, so probably will be this DLL. Okay, but you see the memory also maybe they are good at like trolling the static and analyze too. So maybe they have the obfuscation. So they maybe have some like code like execute maybe hidden by the author. So they will make the static analysis like difficult. So it's possible, or they will do the packing. So packing them means the code will be compressed and then encrypted completely. So if let's say we have the originally have a code and then maybe we have original maybe slightly recap about how to execute, or if you know the OS, then if we have originally we were going to execute, okay, let's say comes in, then we will execute certain things like content, strings, other information. But when they pack, they will have the pack the full program file. Then when they go to execute, they will have another program. So they'll pack it together and then they're not able to see. So mainly when you scan you only able to know, okay, they are originally execute this part, but we are not really scan those like wrap the program or packet. And those like wrappers, they may be unpack or those unpacked code and then one it runs like we call it as a payload. That means that we are generate its own maybe the doc text or the data section from the pack section. So they must like to be unpacked to do analysis. That means like maybe when we do the static analysis, then it may be not possible to figure out. That's why we need to have a more dynamic. But we're going to figure out talk about the dynamic part later for the execution. So those like for the code they unpack in a binary, so it's common. And then we can look, let's say we have the PID. So this will identify common like packing algorithm being like employed. Some of them may be pretty easy. Let's say if it comes out, they say that UPX and then with a certain numbers code, then they'll mix up. And all these like because when we're executing the programs, it will show up for the packing algorithm. And you will see right here, move on. We will have the some tools, maybe let's say we have potential keylogger, the exe. So it's just some example. Let's say we have it. Then we can import using we call the dependency worker. So this one will list all the like those tables. So all the symbol in the DLL, and then we'll put the entries indicate. So those are using for the program. So let's say if you remember, we have the kernel 32, user 32. And maybe for the kernel 32, maybe we have some like core functions, right? We have some function like create directory, create files, create some like certain thread or delete the files like the way. And then for user 32 will be the user interface. Create maybe some buttons, like so dialog, or they show the windows. So you see we have some open certain process, get some like current process, read the files. So all this, and then the programs open other process and files. And we have the GUI program has the GUI 32, share 32, and we will call other programs and user 32. So we'll set the windows like, oh yeah, it's which is some hotkey. So you see right here. So they will grab the active windows and some like key information in this part. And also maybe we can modify the registry. So we have the virtual queue value EX and then virtual set value EX. So right here, that may be possible. That all the way can change it, our content. And for the packed version, so we say, okay, for potential locker, then you will see it will getting less. So all those programs only like appears to load the library, and then they will just pull up the message box. Right here, you can see the difference. Compare, maybe we have to get the modules, load the library A, get the process address, and exit process and message box A for the user. So you will see for the pack, all these under the kernel 32 or user 32 will reduce a lot, and you don't know what are they actually doing. They really execute until they start loading running, then they will pull up load those from the library. And you can compare slightly from the PE views. Maybe we have different section. We say the generated dot text and dot data, and all those data size, let's say size of word data like 7C is right here, and then we'll jump on to the session and then session information for the pack. So start from 000, and then they will show maybe for the text file, data file, just like nothing. And until they really execute certain step, and then it will go higher. So you see the size, it changed a lot. And that's what we mentioned right here in this part. So originally, if we know some like original executable, then we will see all the information they will see. But if we start from the web the program, it looks like smaller, everything you cannot see until in the moment we try to load all the you see right here we mentioned. So we will generate another our own text file and data file, and we have to unpack it. Then otherwise we are not able to see. So until we really unpack it, then we are able to see the file created. And right here, you see maybe for the static NS approach right here, maybe we have slightly difficult and astronomical like growth in the malware variant and then signature. So it keep like going. So it's more like difficult for the single tool or team to handle. So you see right here. And we have more, later we will go through others for checking. I just like skip this part. And just I share some case studies or by the Google, they will provide the virtual total virus total. So you see antivirus stuff right here. So they discuss in the blog post. So you have like accurate by the Google. Okay. And just keep going, share more ideas like for the malware analysis. So another one basic for security, we call the moonshot. So ideas like we can use a massive data set and also like automation for the data science and also the machine learning ML to identify, and then the third attack. So those like third intelligence maybe make like better with the data. So including, so you see they say the data set, they are not only the algorithm but also maybe the key limiting the factors for development of the human level artificial intelligence. They say, okay, let's say they have example is that maybe bank X can use maybe the REST API to kill all the malware and with the bank X. So within its payload to see how is the customer being phished. And when they being used, so in nice maybe it's a real-time detector of a malicious. Okay. What you're talking about, because the REST sometimes we call the REST API. If you have an idea, maybe work on the web programming, maybe work on the API slash, like to get and then to retrieve data or upload the data to the through the content, the payload. So all the queries that we can see is like all the malware, and then we'll know what they sending the data. So that's why you say being fished is all observable. So here's a slightly they upload the foreign APT, and then they will have something called a burning tool for the nation state hacking operation. So it's like also common. So that's why it comes out. Okay, why the cyber commands like latest warning? So it's when the government information effort. So they always like believe to be the first time the cyber commands have like documented. So right here, just like some idea. And also with the virus total, it comes out with some like public service. So they will allow the attacker to know, okay, when their malware have been uploaded and they identify. And also they will provide an like oracle to attack to figure out like how those like bypass your algorithm. So all the content. And then we have more, and then we have the like polymorphism and then metamorphisms. And then the codes can transfer into equivalent, but they can be like different form to the for the static signature. So example right here, the mimic key cut. So they have the meta storage modules. They can like weaponize the some like content specific faith on the Windows. Maybe they will come from like for testing, maybe they have like 100% detection, it goes down. So when they replace it and then we comply it, so it will makes more like difficulty. Okay, also they can might be applied on more like sophisticated algorithm. So they will clustering or like similarity or matching from the machine learning. So that's they try to adding these. The AV is the application we mentioned before. Okay, right here. So we will add the static signature. So we'll be committed that. So that's what we say. So when they apply, okay. And then towards the dynamic analysis, maybe it would like detonate the malware and also experiment the behavior. So it can apply on some like data science or like the machine learning method. So maybe we under the runtime features or some like Google's like searching using the pipeline. So if we have the database table right here, and then we always try to read it, right? Read it, and then we have the collection tables like different rows, and sometimes we can transform it. Okay, maybe one is maybe exact the name start with A, or like sometimes they start with B. So it's called more like dynamic analysis. So based on what we get, and then just like transform it different, depends on what we need, except extract the names, start with maybe different letter. There's some like case study more like the ransomware in 2019. So it's also one of the example. So maybe some like aluminum manufacturing again the NOS. So they also will shut down by the ransomware. And then the machine learning based engineer also can perform the detection for the dynamic analysis. Maybe nowadays we apply more we call machine learning or AI to identify some maybe some new string immediately as a malware. So that's how it works. Later we will practice, but today's mainly just go through all this. But when you look at it for the detection ratio, I cannot say really high, half 25 out of like 69. But we can have different antivirus, and it shows like what's the result and then what's the matching. So right here. So far, just slightly go through and have a quick review of all the contents. And for the operating system, so mainly when for the program in the execution stage, then maybe we need to like do the protection, some also they have some resource allocation. And always we will provide some abstract view of the resources, including the files. Also, we have some system calls. And also, always like in our OS system, when for the execution, we use the virtual memory. So those virtual memory, including maybe some based on the uniforms, the memory space, abstraction for each like process, and also try to give the illusion that each like process have like entire memory space. And here's slightly just like we need to have an understanding of what the OS like talking about. So for the OS, when we create a new process, we have a 5 state, and sometimes when we are not able to completely execute, then we will use the virtual memory space to load it. So including among all other things together. So when we have a system loader, and we will load those executable files from the file system to the memory space. If we remove from our storage to the memory, so they may be done by the DMA called direct memory access, so they access it. And also those executable files, it connects the code, also the some like statically linked library. We'll remember in the execute table, then we including some libraries, also the code contents. And also we have some executable in the file system, so they will be mixed over there and then can be executed again. Also for those. And then also we will load some like dynamic share objects and libraries to the memory space. It can be also like done through the DMA from the file system, also with the original execute file or some like memory mapping. If we talk about memory mapping, because we will put certain content on the memory, and we will have a mapping table, and then based on the address, then we can go to access the content. So all those like can be using by the memory mapping to the existing version. So we can looking for some shared libraries. And when we keep going, doing after we load, then we will resolve the address in the code. Sometimes with the real.text or the real.data. So that's what they generate the text file and the data file. Just a link with what we learned before about the pack. So this is like in the dynamic timestamp window. Okay, so after we load it, and then sometimes we will need to resolve the address in the code when we load those code from the memory. So that's why like every time if those the unpack, we know all those they are all execute. But in the pack execution, then we never know. So right here, the information will dynamically linked to the library. So once the attacker, like the hacker, they want to hack those files, then we need to do the dynamic analysis in this stage. And then once they start the thread of the execution, then they run based on specific entry point, like ELF, so MP header. So if you still remember in the beginning, we quickly go through we're looking for the ELF or like using the P viewer. So looking for the header. So here's what we're looking for. And here's a kind of like is a figure is showing all the content. So when we loading the executable binaries, so always start with the ELF, the header start from here, and including some like program header table files. So when we for execution, and then we have that doc text section and doc data section. It comes out so many times, so it create this like what we always dynamically comes out, and then including some other like .bss section, some like SYM tab or real tag or real text or real data or debug. or other like section header tables. And we always looking for the text section and then the data section right here, maybe including the segments. And for the process, we call the image or executing, and then they have some like virtual address. So here's how actually the OS, when we talk about when the virtual memories included some virtual memory space. So that's how we're going to do the mapping with the memory address. So maybe for the test segment, including the read, and then we can have some execution, or for data segment, maybe start with reading or writing or override. And for the Linux virtual memory space, including some like kernels, like virtual memory, so those like code data heap stack. So those like invisible to user code. So as we know for the kernel, and then for the user stack, so when we execute, then they will create in the at the runtime, including, because here is for the virtual memories, even though it looks like consecutive, and then we have different maybe some mapping tables and showing like which one we should go. And the memory mapping regions right here share some library. So when the library with the link library or some like dynamic libraries, we will go to as a certain address. And in our memory part, like right here, and we have some like runtime heap. So managed by the memory. If you see maybe, I think maybe Java, when you learn Java, so you will use a keyword, I think it's called the malloc, to release the content or to allocate the content. So this one we call the runtime. That means like those like when we execute a program, the functions, then we create the dynamic memories. So it will like access to certain content, and also the read-write segments, including the data.bs. So right here, so they are loaded from the executable files. And they also the read-only segments like initialized doctext, work data. So you see right here all the content when we matching with the like the figure right here. So with the headers and including the doctext section, data section, or .ibs section. So they will allocate to the virtual memory in this part. And when we have execution time, then we will access to certain content. Also, when we execute a program, we also have a link to some libraries. So they will sharing. So we do have some like mapping. We call it dynamic. So we could have a statistical linked library, or sometimes we have some in the execution. We also access to those map common share library. So it's how it looks like. And after we really executing, so you will see some like process when we get right here, we have the mapping, and then or the process with their PID. PID is a process ID. When you execute on the Linux, you can show okay, so what they are really for the memory address, and then the read-write executes. And here's the directory. So what they created, those like linked library and then stacks. So you see here will be like doctext, work data, or data.bs. So here's they will be their memory location. This part will be like consecutive, and then the library will be another part of memory. So just we look like this part. Okay. So what we just look at how the OS looks like on the Linux and all the content. Then the relocation. So we'll be including the static completion. So for those like virtual memories, we have an abstraction. So we make the completion and link it easily. So those linker will bind all the program code and data to actual virtual address. And the linker can design entire memory layout at the compile time. Maybe the Windows, the .com format, so they will effectively memory image. The linker is mainly we can use like when we in the execution stage, if you look at those, maybe the libraries and then the docx, it helps to like blind all the program code. But we need to know, okay, so they need to support the dynamic libraries to save the space. So they do not want to like thousands of like copy of the C libraries on the disk, or like with maybe in a memory. But those like dynamic libraries maybe want to load at the same address. So if those like dynamic library load on the same address, then we need to pay attention. Okay, if override. So also they need to support, we call the address space layout randomization. So for the security, we need to for defense mechanism. So they need to require everything to relocatable at random location. So it cannot be like target easily by the malware. And also those code can support the relocation to any address. Right here, what it's talking about, because when we load the content right here, we have the all the libraries, maybe some like data, maybe some text file. So you see like load on the memory address. Good for the security. If we can update, that means that we can change all those like content maybe in the maybe the library's location. This time maybe it changed to other virtual. So that's why when we're using the virtual memory, it's more like flexible. Then you can create a new one, allocate to another location. So then we update the mapping. If the malware want to do that, okay. If you know, when we try to modify the really low level, sometimes we say the low level, to modify the content, because in the execution state, when we load a program, and then if you want to change a number, we will try to observe the some value or contents memory location, and then when we change their hex number, the binary number, then we see maybe if we want to change, let's say we have a application and then we want to increase the number from 1 to 2, then we will try to search, okay, maybe in this time in the execution state, it increased from, okay, when we try to increase from 1 to 2, then you can able to observe maybe in certain memory address, maybe modify or change. So after we change, then for the attacker, then maybe for memory, okay, they will go to access the same memory location. And this time, if it's about for the bank, so if you want to transfer 100, next time I change to maybe 10,000, then I can change the value. If we supporting the dynamic relocation, maybe next time when they want to change the same location number, it already allocated another address, so it doesn't work. So that's why we try to apply the dynamic way to doing the relocation on the memory address and randomization. So there's a reason. And also we also require some position independence code, the PIE. So when the compiler try to make all the jumps or like the branches relative to the current location or like relative to the like the base register set out at the runtime, this like what we're going to do. And also they require maybe use some like indirections or dynamically generate offset table to determine the address. Just need to remember we try to prevent like the malware knowing the actual location of the like data, so the memory address. So we'll try to maybe like let the compiler to make all the jumps or branches to from the current location to others like relative based on the runtime. Also maybe we'll try to use the indirection or dynamically generate offset table. So one is called dynamic library calls. So it can be done to the procedure linked table PLT or the global offset table in the like ELF in the Linux system. So how it works is just like fill in with the address where the imported library calls when they load it at the runtime. And when the calls to the library function, so they have an index, so into the table. So they determine what the call locations. And they will target by the malwares for the host. So maybe at the L trace. And this part we will cover later. So just like knowing, okay, we even though we try to provide some like dynamic allocation offset for the address, but we still have some way to change it. Okay. As a last part of our class for today, just like quickly show you the final. When we execute, we have the called the EIP, and then we have the register, and then we have some like conditional code executing. And every time, because when we access the data, passing the instruction to the CPU, and then we go to share the address on our memory. We have some our like code data, OS data, including all the in the memory, and then we have the stack like for everything, the code sections statement we're going to execute. And for the EIP over here will be the instruction pointer. If you write a program, we didn't in the OS we talk about some pointers, maybe like program counters, some like address for the next instruction that's included, and then we have some like registered files. So maybe like heavily using for the program data. Also, we have some like condition codes. So maybe those like store the status information, and the most like recent arithmetic operation, or sometimes we use for some conditional branching. So right here, so when we see a branching, we go to certain memory location and access it. And in the memory part, we know like all those like the bytes like addressable array, and then some like code user data, including the OS data, and all those like stacked to support some like different procedures. You see for the malware part, like when we loading everything, because the big picture, the previous figure showing the memory part. So here's like over in our real memory, and also we will have the virtual memory. So virtual memory we will use the second storage. That means our maybe the hard drive, or nowadays maybe SSD. So we use some space to create the tables and loading. When some programs, like when we load the commit files, we'll access to the virtual memory. And if the program, they can support like we call dynamic the with location. So it always every time when we link to the libraries, and then maybe later it will change their location. That's how it works. For the malware too, like for the attacker or for us to do the analysis, you see actually everything sometimes we call the dynamic, or like when we change the memory address location, like even the mapping table when we trace it. So for us, we need to do analysis. We need to check like maybe some real type change, and then for malware, they are looking for some tables offset and trace it and change the content. So actually it's like reversing. So that's why we call that like reversing engineering. So for the malware, they just direct looking for it. For us, we need to go back and trace back. And how can we able to see where the malware modified the content? So far will be the ideas, like just showing you how the malware analysis do, like for the static part, and then when we sometimes including looking for the data. Just like a quick recap, remember for the virtual memories, when we loading key ideas, it's like for the relocation, we should support, even though we sell this one called as like static, including the in the program executions, and also right here with dynamic and static. will be we just looking for the contents directly, and right here we have the preview views, and then look at the size when they load. But it's really difficult. And then dynamic, most of the time when we're loading in the execute stage, and then we'll load to the memory. So why not for the enhance the security, then maybe we require some position independence code, PIE, and also done by the procedure link table and also global offset table in this part. And maybe when you're writing a program, you will never observe, okay, actually working behind maybe the compiler, you see the compilers help you to handle it. And then in the execution state, the OS help you to handle in charge the from the physical memory and then mapping with the virtual memory. So all this will handle in behind. Okay, so far will be today just like for the lecture part. And just like the recap, I think most of you should able install the VM, maybe like different type, maybe the Fusion. If you're using the Windows, will be the workstation, or like the UMG, anything. Because some of you asked me about a question. In the previous lab, I asking you to at least like install the VM Windows system and then install the fair VM. So that one will be working on the Windows. So we are going to coming. We have some labs working on it. So basically, if you are able to install the fair VM and then show me the screenshot and try to take a snapshot on your Windows you already create, then it's okay. It will be enough for the first assignment. I just make sure I hope you have created an environment for our labs. Okay. And if you are able, next one is about the Max, and then for that one will be rely working on the Intel or AMD chips. So if you are just using Windows platform, or if you are using the Apple Intel CPU, then you are fine. You can install that one. If you are using the Apple Silicon, then you are not able to install that one, the Linux based. And if you don't, because I'm still looking for any alternative, anything can bypass it and then can make another copy. If I can make it, then you can install it. Hopefully we can use it later. If you don't have the if I couldn't like solve this problem before the lab, then if you're able to figure out other using another machine or have another desktop, then or later we can share, or I can host, like let's see if I can create like host online for testing, or like have another environment to those can using the Apple silicon chips, then we can test it later. Okay. And let me see how many of you right here. If you don't have any problem to install the VM or create the environment, then that's it for today's class. If you have some question, you can stay to ask or just send me the email so I can help you to solve it. So do you have any question? If no, then we just end our class today. Thank you.
Yeah, I had with that VM with the Windows VM. I think you have to run an advanced option whenever, for Windows at least, whenever you get the ISO file, you have to then run it in boot mode to initialize the Windows 11 VM. I know that I had struggled with that. It's still not quite how operational because I'm still trying to figure out the boot stuff, but definitely close on getting that Windows VM operational.
Okay, yeah. Yeah, some of I know for the because for the VM, because when they load, it happened to the my Apple Silicon. If I load in the we are testing with the Ubuntu system too. Sometimes when I execute it, I also need to load it the ISO file in the boot mode. Otherwise, it's just stuck. Temporarily in this stage, if you cannot solve it, then just try to like load it in this moment and let's see. I can check for the Windows because I didn't I need to use another computer to test with the Windows. So I can give you a solution if like how can you bypass it? Like you don't have to like loading the ISO every time. Because for the Apple, it doesn't have a let me show you right here the VMware. Yeah, I think for the Apple user, maybe you don't have any issue, but mainly for the because for me when I loading the Ubuntu, it requires me to load in ISO. So slightly have this problem in this moment, so we can try to see. Blocking the fix VMware permission by in contact. Okay, so if you have some issues to install it, because I try to set the deadline, but just like don't worry about it. So once you're able to, still maybe if a week, let's see, I will
I want to say
actually I
it's
want
due
to.
by the 30th, and if I'm gonna continue to try because it's on my laptop versus I'm on my desktop right now. I'm gonna continue to
Mhm.
try it, and then I'll
Okay.
email if you have if I hit a crossroads, Professor.
Okay. Okay. Good. Good. Yeah, I will check. Maybe I'll send an email or give me a feedback. Because like coming on Thursday, our class actually I want to do something like at least like to start to execute. Last time we stopped by is they asked you to install the fair VM, and then I asked you you can download the malware file from the GitHub. Like you can download it, but don't unzip it. Permission. Okay, good, perfect. Okay, somebody got it. I can slow down if you couldn't install it. Just let me know. So I will see how many students start this process. Then maybe I will slow down. Maybe just like go through some like boring lectures. Go with some idea. So I'm trying to set up the free VM. Well, because disable Windows Defender. Okay, man. Um, for yours, did you turn on? Because sometimes it's like temporarily, but sometimes you have to do it. Did you turn on from the? Let me start it. I just shut it down. For the Windows, for the real time. Okay. So is it always happen to you? When you like temporarily close it, then let me see. This one. Let me see. I have created. Nothing. One second. When you install something, it create a new copy. So it takes some time. When you disable, okay. Let me see. I forgot the pin. Okay, is this reload the defender. Okay. Then I'm still trying something, so it's still executing. Let me see the Windows. So are you the only one or anybody also have a same issue? That means like when you try to turn off the Windows Defender, then it just like enable itself again. Let me see when you're executing, close it.
Professor, on a side note, will you let us know if you'll do online
Mhm.
class on Thursday, or if you, I guess, you get your vehicle by then, you'll send us another email or message to say that we'll be in person on that day?
Um, Bill, I still not yet. I still need to contact with the body shop. But so far, if you didn't receive the new update, then we try to host it as an online like this. Then you won't always receive my email saying,
Okay, so
do you
just
think it
expect
sounds good?
online for now until you get your problems resolved then?
Yes, yes.
Okay. All
Okay,
right.
yeah.
Thank you,
So
Professor.
then, yeah, so it will be better. Then you don't have to always like receive my email say, let's do it online in this time. Okay. And did you turn it off from the setting? You just turn off the real-time protection, right? This means I know when for the Windows some when you turn off the real-time protection and let me also turn off the cloud both. Okay. And if you it's still like popping like enables again, maybe you can try to add the exclusion and let the because sometimes it has the execute files, but at least you maybe let it being execute. So maybe you can add the folder, so access to it, and you can go to downloads and then select this file, and you can try this one. Try it doing this way, adding exclusions and also turn it for the virus and first protection setting and try again. Okay. And let's see if you can solve it. And anybody here have other problem? And I will, before the class, probably tomorrow, maybe I will see and check again if like most of them most of you like still working on the like VM or like installing it, then maybe I will postpone the lab maybe to next week, so you can have a extra time to install or set up the all the applications. Okay, and I will see if I can solve the problem for the Linux one. Okay, if you don't have any question, then I will end the meeting for today.
I have a question, but it's about
Mhm.
smart things. Is that okay?
Yeah.
So I have a Raspberry Pi and I can SSH into it for the lab. Can I just show the SSH or do you want like the screenshot of the Pi?
Um um you when you using SSH and then you make the screenshot like of the connection, it's okay. And if you look at my slides and then I record the video, I will add extra one more thing is the encryption, right? You using the try to using the OpenSSH to generate the key. So I wish like if you can able to like one more step, then if you can show me this one too, like you already
Okay.
generate the key. Yeah.
Okay, awesome. Thank you so much.
Okay. Yeah. And then that's it. Yeah. You don't have
Yeah.
to like create the like open the GUI showing the Raspberry Pi. Okay.
Cool.
Okay.
Thank you.
And okay, thank you. If no other question, then I just stop right here and the sharing. Thank you.